Hello, welcome back for section 2. I'm glad you're back. You've been probably thinking about geologic principles and laws even if you hadn't really planned on it. If you've done any type of travel, even in your local area, I'm hoping that you saw rock layers, even the rocks on the ground, maybe with a little bit different perspective than you did before you took section 1. Hopefully you've read section 2 before we get started. This is a very important topic called Dynamo Earth. Almost sounds like a superhero, doesn't it? Like Shazam or something really wonderful out there, like Iron Man or Captain America. It's kind of like that when it comes to planets. So we're fixing to learn about Dynamo Earth and tell you all about it and why it's so special. And we're not the only planet that has it. Why do we have the name Dynamo Planet for Earth? We're not alone in the universe nor the galaxy. If you want to be frank, not even the solar system. At one point in time, there are other planets that have had this special dynamo structure. So when you think about dynamo, man, it's really cool. I get all excited because if we didn't have a dynamo relationship between the inner and outer core, with the inner core being solid and the outer core being liquid, we would not create a geomagnetic field. Boy, life as we know it, folks, would be a true bummer. You and I'd be floating out in the middle of space and not liking life too much. We'd be out of commission, if you get my drift. And we would be drifting afar because life gets held here by gravity, and that gravity is a big part of understanding and appreciating this geomagnetic field that has been created for us. So think about just even the solar radiation that could literally char us if we didn't have that protection. We have an atmosphere that allows the atmosphere to stay intact, which is important to evolution of life and preservation of life. So, and not to mention weather, which is important to driving the rock cycle, which you'll learn about, and a little bit in sedimentary rocks, and then again when we get to the rock cycle in section 9. So let's talk about the different parts of the inner Earth and the crust and explain how they're interrelated. Because you hear all about the mantle in particular when people are talking about plate tectonics and how cool it is that we can have plates that move and drift. Well, without this special relationship of the core, the solid inner core and the liquid outer core, it just would not be possible. We got to start at the beginning, back when our planet was just coming together. And you have to imagine in the solar system, when the sun was born and forming, just massive amounts of material being ejected into space. And as it was being ejected, the heavier elements actually stayed closer to the sun and the lighter elements got drifted off into space. And that's one reason we have two very different types of planets in our solar system. We have the terrestrial planets that were Mercury, Venus, Earth, and Mars. And then we have the Jovian planets, which of course is Jupiter, Saturn, Uranus, Neptune, and if you've been paying attention, Pluto has had some interesting developments because it got kicked off the planet list and it's looking like it might get back on. So kind of a fun thing there. But anyway, the Jovian planets are made more of gases, and they are not the same in terms of their spacing, their proximity to the sun. They're much larger, spaced farther apart. They have more gaseous composition, and our terrestrial planets have these denser rocky materials. So let's get to that denser rocky materials because that's all about differentiation. So let's think about what that word is, differentiation. Let's take the root word of different. Different elements at different places inside of the earth. How did that come to be? So as we were being bombarded by meteorites and all this debris was in space, eventually enough mass came together. The denser elements sank towards the middle of the terrestrial planets like Earth and created a layer known as the core. And then you get lighter elements that were on each layer subsequently up to the crust. But we didn't have a crust to begin with. We only had a molten Earth. And so it would take a while before we could delineate these different layers, like the solid inner core, the liquid outer core, the mantle, and then eventually get to a point where the outer shell of the Earth was no longer molten, it was actually crustal material. And that would allow us to start developing igneous lavas and that sort of stuff, which would allow us then to also create weathering patterns once we had an atmosphere in place. So how do we really know what the inside of the Earth is unless we've actually been there? Because I know in the movies sometimes it shows that we've been to the inside of the core of the Earth. It's just not happened. Well, what has been there are seismic waves, earthquake waves. So to determine the Earth's composition, there were some scientists that were pretty darn important. One of them was by the last name of Gutenberg. The other one was Milankovitch. Each one had a very special role in determining places in the Earth that are notorious for having different composition from the layers on either side of it. The way we discovered this was with seismic waves. They were studying, these scientists, how seismic waves travel through earth and material, and we can duplicate that in a laboratory setting with just about every element known to man. Also, I might add to rocks and minerals. We can test them and see how seismic waves travel. So they kind of have like a handwriting or signature pattern. If they hit, let's say, iron, or if they hit nickel, or if they hit silicon, or if they hit sulfur, or something like that. So they're going to have a special little signature pattern. And those waves, that can tell us what that is. And when those waves make that little signature pattern, scientists can go, hey, I know what that is. Now, cool thing, there's two body waves when we're talking about seismic waves. Body waves travel through the interior of the Earth, and then there's surface waves we'll learn about in earthquakes later in the semester. They travel at or near the surface. But P and S waves are body waves. So P stands for primary, S stands for secondary waves. P waves are always the first to arrive during an earthquake, and they also travel at the fastest. They travel at approximately, on average, 8 kilometers per second. And then S waves are known as secondary waves. They're always the second to arrive on the scene in an earthquake, and they travel at an average speed of 3.5 kilometers per second. Definitely good test questions to know there. Why is that speed important? Because the first arrival time of P and S waves, when it comes to earthquakes, that'll be important for us locating the epicenter. But in this particular case, P waves can travel through solids, liquids, and gases. Well, S waves are a bit more picky. They only travel through solids. So if we have S waves that can travel through the Earth's crust down through the mantle, but they don't penetrate through the core, that would tell us that there's some kind of liquid material that makes up that place where they no longer can travel, which happens to be the outer core. P waves, however, do travel through all of those things, but when it hits the outer core, their signature pattern gets very special, slows down a little bit, and it has a signature pattern of iron and nickel. So the core, both pieces of it, definitely have been indicators that we have a very dense type of core system with a different type of mantle composition. So the boundary markers between the core and the mantle is a special thing. We call those discontinuities. Speaking of discontinuities, these are the places on Earth where we have that composition change that we can document with P and S waves, with seismic waves. And there's multiple discontinuities, but two are by far the most famous, the ones I have highlighted here. So there's one between the crust and the top of the mantle, and then there's one at the base of the mantle at the top of the core. And so we're going to talk about each one. And the first one we'll talk about is the one closer to the surface. We call it Mahoveric, which is the name of the last name, that is, of the guy who discovered this particular discontinuity. Since hardly anyone can spell the name, most geologists just refer to it as the Moho. And so the Moho is that discontinuity between the lower crust of lithosphere and then the upper mantle. And there's a definite composition change with P and S waves as they travel through this material. So in other words, that signature pattern is different. I'll use an example that most of you can relate to. So on geology field course, my students have to ride in vehicles and they'll be taking notes in their notebook. And, you know, we might hit a rumble strip and it goes and everything just starts jiggling and their notebooks will look like, oh, you know, looks like somebody just did hieroglyphics in it that nobody can read, and they're like, okay, Elaine, you gotta not hit that rumble strip again, or we'll change pavement type, and it'll change the way that they can write in their notebooks. So it changes maybe their signature and writing patterns. I would say the same is true with P&S waves. They have these special signature patterns for each type of element and rock material and minerals that they're traveling through, so we can actually determine what the composition is of that material without ever seeing it. In the case of the moho, there's several places on Earth where some of this has been shoved up to the surface to study. Other places, countries around the world are trying to drill down to the moho because if its composition is different, that means there is potentially items of intrinsic value, meaning maybe it's metals like ores, or maybe it's some kind of inclusion like a diamond or something that we don't find in the crust at much in any kind of great concentration, or maybe it's something completely new that could be important for industry. So the Gutenberg discontinuity is the one that's between the outer core and the lower mantle. That's this one down here. Another name for this is the core mantle boundary, or the CMB. That's Charlie Mango boundary for Bravo. So let's talk about this one. This discontinuity is where the S waves disappear. I guarantee you that's a test question. Why is it so significant? Because S waves bounce off of this because they cannot travel through liquids. But the P waves continue to travel on. They just have a new signature pattern. They actually do slow down, so there's a density change in the material that they're traveling through. So that's an important element of really understanding this incredible composition of the Earth that we've not necessarily seen, but we can document with science. So there is a lot we can know about the inside of the Earth, even though it's so deep down there. All right, let's talk about each layer of the Earth from the inside to the out. When I was taking geology for the first time, my professor just breezed right over the Earth's core, and I never really got it, how important it was, until long after graduate school. And I was like, everybody talks about the core, big deal. Let's get to the mantle where all the action happens. Frankly put, you can't have the action of plate tectonics and plate movements and hot spots without having an active core. So I've got good news and not so good news. The good news is we still got a lot of time left for our core to do its business in terms of its heat giving capacity, but it is diminishing over time. We have a couple of billion, as in Bravo, years left before the Earth's core kind of dissipates completely and plate tectonics quits to operate the way we know it as today. So where is that heat coming from? It's coming from the decay of radioactive elements found in the core. Because remember those heavy elements I was talking about that sank down into the inside of the Earth? That magic experience of them giving off that energy, that heat, like a thing of plutonium you see in the movies where people touch it and it's hot. That's a real thing. That's heat that's giving off from radioactive decay. So that the core is making that happen. So remember, we have a solid inner core and a liquid outer core. I know it seems a bit backwards, but it won't after we go through this process. So remember, the core has 16% of the Earth's mass. That means we have a remaining 84% that we haven't talked about, and we will in a minute. So I do want to address, why is the inner core solid and the outer core is liquid? It is certainly hot enough inside the core, inner core, to be liquid. But the pressure that's placed upon the elements down there is so immense that it cannot be in a liquid form. So the inner core stays solid and the outer core stays liquid. And again, that heat is coming from the decay of radioactive materials. So between the outer core and the mantle exists that important discontinuity called the Gutenberg. Let's talk about the mantle. So this is the part that you'll hear most instructors go on and on and on about, is the mantle, for a couple of good reasons. It makes 83%, so let's add 16 and 83, that puts us at 99%. Which means we still have one little loner percent that needs to be accounted for in terms of the Earth's mass. We'll get to that in a minute. So the mantle accounts for 83% of the Earth's mass. If you add that to the mantle, 83 plus 16, or subtract it from 100%, either way, you'll get one little percent left. Just 1% left, and that'll be what the crust constitutes. There are 3 important layers of the mantle. We'll start from the bottom. Remember the law of superposition? You always start at the bottom. So the mesosphere is the lowest bottom layer of the mantle, made of peridotite, which is ultramafic igneous rocks. We'll get to that in section 5, why that's such an important material. And it is the densest part of the mantle, not the core, the mantle, because the core is obviously the most dense that we have on Earth in terms of layers. But it is super dense. It's a very rigid material, unlike the layer that sits right above it called the Asthenosphere. The Asthenosphere is where so much of the action happens with the generation of hot spots, which is where you get a mantle plume that rises up like a lava lamp and comes up through the lower lithosphere. So what's the Asthenosphere like? It's more plastic-like. Not necessarily liquid. If that were the case, S waves would not be able to travel through the Asthenosphere. So I'm not telling you that it's all one perfect plastic kind of rocky material. I'm letting you know that there are probably sections of it that do have molten material, but it is certainly more rock plasticky, like Play-Doh or Stretch Man that you can play with and it gets warm and it moves pretty well. That's what the Asthenosphere is like. The lower lithosphere, which is the top layer of the mantle, is called the upper mantle. So you're like, why aren't they called the lower lithosphere? It'll make sense in a minute. This is another area of rigid rock, but it's not nearly as dense in composition as we have that ultramafic rock that makes up the lower mantle known as the mesosphere. Instead, we get mafic igneous rocks there, so they're not quite as dense, but they're still a lot more dense than what we have in our crust. So we're going to be looking at all 3 of those in comparison to the lithosphere crust that we're fixing to see. So let's talk about the asthenosphere and hot spots and why there's such a big deal about the 2. Remember, the asthenosphere is a place where we have plastic-like rocks, and the reason we do is there's a lot of convection cells there. So in most textbooks and even diagrams that you can find in literature and science articles and things of that nature, you will see that it looks fairly simplistic, of just a nice little round circle like a recycling symbol. The truth is, more scientific studies are being done on convection currents, and they're fairly complex. No 2 are exactly alike. So I would be not doing you a favor by just giving you a generic diagram and saying, hey, they all look like this. That's not true. That's why our hot spots behave differently, in addition to composition of the material that the hot spots are melting to help add to their plume size. Right now, currently, there's about 40 to 50 active hotspots across the Earth. These hotspots dictate how fast, how slow, and in what direction plates move. So we have a hotspot wells up and crust separates, begins to pull apart. That creates what we know as a divergent plate boundary. So wherever one pushes away from another, eventually it's bound to bumper car into and crash into another plate. Well, that would be a convergent plate boundary. And sometimes the plates just move side by side like this. And if they do, then you would have a transform plate boundary. But nevertheless, hotspots are what makes the story of plate tectonics happen on Earth. And it's also responsible for the volcanism that we have happening on Earth. So that brings us to the top layer of the Earth's surface, that one lone percent that we were talking about a little bit ago. So to kind of recap on the mass of Earth, 16% was accounted for the core. That's the inner and outer core combined. 83% was given to the mantle. And just that little bitty 1% makes up everything that we know, meaning everything that you and I can relate to, the stuff we walk on, stuff we drill for, that's all the crust. So the lithosphere represents the outermost layer of Earth, and it constitutes two different things. So you get that upper mantle that we were talking about, then you get the Mohoveric or the Moho discontinuity, and above that you get what's called continental and oceanic crust. So this diagram, I really wish it was a black color right here where it says oceanic crust, because that's the color that oceanic crust is, and then a lighter colored gray for the continental crust. But you can see the lithosphere has that upper mantle and all of this stuff with it. So that moho is that boundary between these two sections right here. So the Earth's crust is just that little bitty 1%. There are two different types of crust that we need to address. There is continental crust and there is oceanic crust, and there's a big difference in the way they behave, their age, their thickness. So let's just get right to it. This diagram that's in your book, I had the publishers make oceanic crust really dark. It took me a while to get them to understand how very different in thickness and in composition that this crust was, and I finally convinced the graphic artist to do this. So you can see it's very dark, almost black in color, which is very accurate when you pull rocks from the bottom of the ocean. And it is thinner than continental crust. So I would use the example of marshmallows for continental crust, light in color, thick and buoyant, and then you get, let's say, a Hershey's bar, and when the two collide, the Hershey's bar is going to be more dense than the marshmallow, so it sinks beneath it. That is an important process for why we have what's called subduction zones around the world. Let's talk about on each side, continental versus oceanic. Continental crust is granitic, meaning it's granite-based. So you'll learn about that in igneous. It means it has a lot of feldspar and quartz and silica-type minerals in it. It's lighter in color and not as dense. While oceanic crust is mafic, it's typically made of what's called basalt, with the B as in Bravo, and gabbro, which is like granite. And then remember that oceanic crust is much denser, so it would be like having that candy bar, that Hershey's bar, hitting a very light marshmallow. So the marshmallow would be the continental crust, and the Hershey bar would be your oceanic crust. Now, continental crust is super thick in comparison to oceanic crust. On average, it's about 35 kilometers. But where we have our major mountain ranges, let's say like the Himalayas, even if you talk about the Rockies, the Andes, we're looking at they can get up to 80, 90 kilometers thick, maybe even 100 kilometers thick under your mountain ranges. And the thinnest parts of our continents actually are where the continental shelf tapers off into the continental slope. Well, oceanic crust is thin in comparison to continental crust. So at its greatest thickness, it might get up to 10 or 12 kilometers thick, but on average, it's somewhere around 7.5 kilometers. And the reason is most of the ocean crust is derived from mid-oceanic ridges where hot spots cause the ocean crust to separate and magmatic material comes up to the surface. A fourth way that our ocean crust and continental crust differs is in age. So part of the story I'll hold on to for plate tectonics, but continental crust, the oldest terrestrial rocks, meaning they didn't come from outer space, they were made here on Earth, date back between 3.8 billion, that's B as in Bravo, to 4.2 billion years old. So some new discoveries have surfaced some rocks that are older than the oldest one even 10 years ago that have been documented. So even 10 years ago, 5 years ago really, 3.8 billion was considered the oldest rock. But now we have some contenders that can be right around the 4.2 billion years old, and they're not meteorites. Well, ocean crust is a totally different ballgame. The oldest oceanic rock cores that have been taken out from the deep sea drilling program, and they've drilled all over the ocean floor from continent to continents and all the way across the oceans, is 180 million years old. That's with an M. Wow. That's a little tiny number compared to 4.2 to 3.8 billion years old. So that makes you wonder, why is the ocean crust so young as compared to continental crust? Why is that not billions of years old? And you're going to find out in section 3. So hold on to that thought. Regardless, we have this important relationship because of the hot spots that are on Earth. We have plates that are slipping by each other. For example, the Pacific plate over here is sliding next to the North American plate. It's moving in a northwesterly direction while the North American plate is moving in a kind of a southeasterly direction. Here's Juan de Fuca here, an important plate because it's pushing into North America. Well, how can it do that? The only way you'll have that is if it's having some kind of separation relationship, like a divergent plate boundary with the Pacific plate. The Pacific plate is making a nosedive. In other words, it's crashing into the Aleutian Trench in Alaska. Here's a good example of another important relationship. Works just like this one up here. The Pacific plate is pulling apart from the Nazca plate, which is right next door to the South American plate. Well, it's doing so at such a fast rate that it's pushing the Nazca plate into South America and faster than any other known plate at the current day and time. So I can only think of one plate that's probably moved faster that I'm aware of, and it's this one right here. The Indian plate, or India plate, used to be way down here when a bunch of continents were together, called Gondwanaland, and it broke off and made a rapid sprint across the ocean basin until it smashed into Eurasia, which is, I might add, still smashing and still uplifting the Himalayas along with the Swiss Alps and all of these mountains that are in Europe area. My point is that all of these plate movements and arrows are dictated by hot spots, which are coming from the Asthenosphere and heating up the Lithosphere, causing plates to move. So the plates are going to continue to move around as long as we have that heat capacity, and that heat source is coming from the core. So when you look at all the plates together and you see the relationships they have, this is a diagram out of your book, we create every different type of plate boundary, which you'll learn about in plate tectonics, as a consequence of plates moving around on the surface of the Earth, which dictates the features we see geologically. So that could mean something like a mountain versus a volcano versus an earthquake. Let's say that we have areas of the ocean floor that are really flat, like an abyssal plain, yet we have guyotes and seamounts at the bottom of the ocean floor. And then we have a mid-oceanic ridge, which is the largest mountain range on Earth by far, certainly the longest stretching one. All of these are caused by this remarkable activity that's causing the lithospheric plates to move around and create geologic features. So what are some key points about our lesson today? Dynamo planets, specifically Dynamo Earth, they were created by differentiation. That is a test term for sure. So differentiation is where you get your heaviest elements and your minerals that start sinking to the interior sections of that planet. In our case, it was lead and nickel, and then we have a few other lighter elements with that. So differentiation caused our inner core to be solid and our liquid core to be liquid. And as the liquid core spins and when we rotate around our axis, it creates that important geomagnetic field. If there's one takeaway from today's lesson is you should be very grateful and thankful we have a dynamo planet, because you would not likely be alive unless you were blue-green algae, and even then it would be a highly unlikely. You might though, you might survive, but the rest of anything living at the surface would probably not make it if we didn't have our atmosphere intact and protected by our geomagnetic field. Remember the different masses of the Earth. The core makes up a total of 16%. The mantle makes up 83%. So remember, the core has two parts, the inner core that's solid, the outer core that's liquid. The mantle has three layers, the mesosphere, which is the bottom, the hard, rigid stuff that's ultramafic. Then you get the asthenosphere, which is the plastic-like section where the hot spots, most of them, originate. And convection currents are moving that material around. Then you get that upper layer of the mantle, which is going to be the lower lithosphere. So those three parts together, there's a little discontinuity that separates them called the moho, and then we get the crust. And remember, there are two types of crust. There's continental and oceanic, two very different types of behavior patterns in terms of their thickness, their age, their density, their color, their composition. All of that's important to know as key takeaways from this lesson. Getting to the continental and oceanic, I really want to kind of home in on the key stuff. Remember, continental crust is very old geologically speaking, billions of years old, where oceanic crust is up to 180 million years old maximum. Continental crust is thick, while oceanic crust is really thin. Continental crust is not very dense as compared to oceanic crust. And there's a reason oceanic crust is more dense. It contains more mafic and ultramafic minerals and elements. So it has more ores in it, like iron. So it's more dense, and it's going to always sink beneath the less dense crust that's continental. Remember that continental crust is made out of granite-based material, which is lighter in color and not as dense, while mafic-based stuff is what makes up our oceanic crust, darker in color, mostly black. Sometimes you might even get a green tint, which makes it ultramafic. So how does this all relate to us moving into plate tectonics in section 3? Well, first thing I want to point out right here is you're looking at an active divergent plate boundary where two plates are pulling apart in Iceland. I took the shot. It looks like something out of the Hobbit or Lord of the Rings, doesn't it? And that's what I thought when I took the picture. I was so struck by it. But what you're seeing here is the North American plate moving this way and the Eurasian plate moving this way. So these two areas used to be joined about 10 to 15 million years ago, and that's how long it's taken for these two plates to pull apart that much. Eventually, Iceland's just going to split into pieces, and we're going to have a brand new mid-oceanic ridge there. So why is it moving? Why is it pulling apart? Well, it's pulling apart because of a hot spot. And that hot spot comes out of which section of the mantle? See if you can remember that. Was it the mesosphere, the bottom part? Was it the middle part called the asthenosphere? Or was it the upper part called the lower lithosphere? And the answer is most of the convection comes out of the asthenosphere, pushing these hot spots into the lower mantle and then into the upper, or into the lower lithosphere, actually, and to the upper lithosphere, which is where our crust material exists. Do you see this dark black color? Well, this may look kind of gray to you, but it's black, and I will tell you that in the oceans, the stuff is darker than that when the lava material that comes up to the surface, and it's because it's coming out of the mantle, which is very mafic. Before we wrap it up with our nature moment, I'm going to give you what I call my science serving of the day. So in just about every lecture, you'll have one or more of these little clips that I do on one of my excursions, like a field endeavor, a sabbatical, or something, some trip I've been on, to give you a flavor of some kind of geologic thing. Most of the time it relates to exactly what we're talking to. Sometimes it's not a perfect fit, but it still has a relationship to everything we're covering in the course. So let's give you one of those now. Welcome to Crater Lake National Park. Crater Lake is located in Oregon, and the big question is, why does it look the way it does? Crater Lake is the result of ancient volcanic eruptions that actually had such power that they blew out a lot of magma, lava, very, very quickly, creating a caldera, which is a very special geologic feature where the volcano collapses inside of itself. The eruption that caused this occurred approximately 7,700 years ago, but has evidence now of recent volcanism in the form of the volcano that was just indicated to you. That volcano is Wizard Island and represents resurgent caldera activity. Whenever you see that, that should send a flag up. Notice the light-colored igneous rock. That's very, very characteristic of any subduction zone around the world because you got blending of basaltic and felsic crust at a subduction zone. When you look at Wizard Island, it shows evidence of very recent eruptions, even the lava that's capping the flows at the top there. That should be very indicative of a dangerous situation anytime you see resurgent activity growing inside the floor of a caldera. So, all calderas basically have the same shape. They're circular. When you get this zoomed out view, panoramic view of Crater Lake, you'll begin to see there's a big gigantic rim. You need to imagine that that magma chamber collapsed inside of itself. And that's why these basically have the same shape around the world. Not all calderas are filled with water like Crater Lake, but all calderas represent ancient volcanic eruptions. So the next time you see one, you'll know how it formed. This is truly a volcanic legacy. See you at the next stop. Bye. You have a pretty good idea how Crater Lake formed. A lot more to the story than meets the eye. I'd highly encourage you to go visit Crater Lake at Oregon because it's really it's fascinating, it's beautiful, and wow, stunning, gorgeous geology and landscapes. Be careful when you go what time of year because it can be snowy even in June, just as an FYI. So as we end our lecture experience on dynamo planets, we'll conclude with something kind of fun, which is stuff about blue penguins in New Zealand. They're the smallest species of penguin in the world, and they have a natural habitat on the east side of the island of the South Island of New Zealand. But there's a place that's in Christchurch, that's the Antarctic Center, and they have a habitat designed for blue penguins who have been injured and are disabled. They can't live in the wild. So they have this little home for them, and it's kind of a cute place to see how they take care of them and how much personality these penguins have.
Trying to lay eggs. How you going here, you guys? So the ones that haven't got partners, they find it a little bit hard. Always trying to find a partner, but we only take animals, of course, that are injured. We can't say no, we won't take any more girls. We never turn a penguin away. They do have to be pretty life-threatening, their injuries, before they do come here though. I can kind of tell when Turk's had enough because her wee belly does get quite large and full. And I think she might have just, that's it, she's thrown that one up. You can see she's going to start to shrink a little bit and baby's going to steal those fish because I won't feed her. Good thinking. So this is Turk's nice and full now. As you can see, it's like Christmas, and she's very lazy. You have enough to eat now? Do you want to get down? Like you go swimming for an hour on that full tummy. Okay, so this penguin here's our new one. This is Horatio. She's trying to learn how to eat like the other penguins. She's doing quite well, considering she's so young. She's still got her young coat of feathers on. She's still got her fledgling coat. She does have to lose those. I don't know if you'll eat this one. It's a very big fish. Oh, yep, you're going to eat that.
Remember, you need to come back for section 3 of plate tectonics, and that'll be happening at our next stop, and I will see you then. Bye.